Audio is good. We're ready to go. So I'm going to be continuing today talking about duality. Last time I introduced you, I gave you the formal proof of strong duality and showed you how to sort of generalize from standard and canonical form to arbitrary linear programs. And I first sort of wrote out a long, sort of messy, sort of algebraic representation. But here we have the sort of the cookbook for performing transformations. And last time I showed you this duality transformation that showed that a shortest path problem was dual to a unit min cost flow problem, right? That the shortest path from S to T was the cost of sending 1 unit of flow from S to T. And this emerged just from mechanically taking the dual and interpreting those dual variables as a different characterization of exactly the same problem. Right? And this is one of the most wonderful things about duality, is that it gives you for free another way of looking at a problem. So even if you don't use it algorithmically, you can use it for insight. We will see later that there are also many ways that you can leverage it algorithmically. But I want to start with some more insight by looking at another duality problem. And what we're going to do first is max flow. So let's look at the max flow problem and think about it as a linear program, okay? So actually, I'm going to turn it into a circulation problem to make the to make the notation a little bit simpler and cleaner. So I'm going to add, wow, sorry, my pad is behaving strangely. I'm going to add a TS edge. And I'm going to look for a circulation, maximizing the flow from T to S. Does everybody see why this is just another way of making it a max flow problem? Okay, so let's use variables xVW for the flow on edge VW. All right, and can people tell me what this linear program is going to look like? What's the objective function?
Max XTS.
I hear nothing. Did my speakers go down again? Can somebody talk?
Your speakers went down again.
Yep, that's what I thought. Okay, try again. Can somebody speak now?
Hello, can you hear us?
Yes, good, thank you. All right, so what's the objective function for this max flow?
Max XTS.
Exactly. So W star equals max of XTS. And now what are my constraints? What do I need for a feasible flow?
Conservation, so net input into a vertex equals net output.
Good, net input equals net output. So what I will write that as is the sum over all W's. there's a ghost in this app that keeps turning on my eraser. XVW minus XWV is equal to 0. And this is true for all V. And this is why I introduced that edge from T to S, is that now I don't need to do special cases for vertex S and vertex T, right? I have balance everywhere because the flow from S to T goes back on the TS edge in a circulation. What other constraints do I need?
All the XVW are less than the capacity of that edge and also
Exactly.
non-negative.
XVW is less than UVW for every edge, right? That's the capacity constraints. And we also require that all of the flow values be non-negative. Yes? Okay, we have a linear program, right? Now, how do we take the dual? Okay. So actually, again, if we look at the cookbook, simply for notational convenience, I'm going to refer to the maximization problem as the dual. So we're actually going to build the primal. Okay. And since the dual is a maximization problem, the primal is going to be a minimization problem, right? So what are we going to minimize? What should the objective function look like? Where do we find it looking at the dual, the first linear program? Right, where are the coefficients that are going to show up in the objective function?
All the UVWs.
Good, so where did you find them?
On the right side.
Exactly, the coefficients of the objective are the right-hand side numbers in the constraints of the dual, right? And so you pointed at the UVWs. Remember that there is going to be a variable for each constraint, right? So actually I should talk about that before even writing the objective function, right? There's going to be a variable per constraint. Right? So we have two different kinds of constraints. We've got the balance constraints and we've got the capacity constraints. Right? And so let me write, notice that there's a balance constraint per vertex and a capacity constraint per edge. So similarly, there's going to be a balance variable per vertex in the primal and a balance and a capacity a capacity variable for each edge in the primal that I'm building, right? So I'm going to have, I'll call the variables associated with the capacity constraints YVW. And also ZV for the balance. Okay. And again, this is what you'll typically do, is that you'll have different kinds of constraints and you'll define a different variable for each kind, which indexes over the occurrences of that kind of constraint. Okay. So now that I've got them, I can start writing down my linear program. Okay. And as was said, the coefficients that I see are going to be the right-hand sides of the constraints, and those are going to multiply the corresponding variables. So what is my objective function going to look like?
The sum of the product of UVW times YVW.
Exactly. So UVW are the coefficients and YVW are the variables. What happens to the ZVs?
They just get multiplied by 0.
Exactly. Their coefficients are 0, so they don't even appear in the objective function. Okay. Now we need to talk about the constraints. Now, to think about the constraints, you need to think about the constraint matrix, right? Because essentially taking the dual means transposing the constraint matrix, right? In the first linear program, if we think about multiplying with the vector on the right, each constraint corresponds to a row, right? In the second linear program, the one we're calling the primal, we're going to multiply from the other side. Each constraint is going to correspond to a column. So what we do is we fill in the rows by looking at the first linear program, and then we understand what's going to show up in the columns, right? Now, as I said, there is a row per constraint of the first linear program. So those rows also correspond to the variables of the second linear program. So we're going to have some YVW rows and some ZV rows, right? That's just shorthand for the constraints that they correspond to. So what shows up in a particular YVW row? That is the row that corresponds to one of these capacity constraints, right? So what do we see in that row?
A 1 for each edge that it's showing the capacity for.
A 1 for each. What do you mean by an edge that it's showing the capacity for?
So it's saying like XVW is smaller than UVW. So maybe a coefficient of 1, and the line describes it for XVW.
Exactly. We're going to have a diagonal matrix here, right? Because when I multiply one of these upper constraints, it's going to be bounded by the corresponding UVW, and all that we pick out is a single XVW value. So there's one row for each edge, and it's an identity matrix. Okay. Now, what about the balance constraints? What sort of rows do those turn into?
So if we're looking at node N, or maybe V, if we're
Node
looking,
V, right.
for each node that has an edge going to V, we're going to have a 1 at that row.
Yep.
And for each node that has an edge from V, we're going to see a -1.
Almost exactly right. I would put it just the opposite way. If we look at the coefficients on the balance constraint, you'll notice that edges leaning from V, right? Those are VW edges. Those go with a +1. And edges leading to V, edges that form WV, those have a -1, right? So basically, we're going to have a series of +1s and -1s in this row. And it's going to be a +1 when the edge is, it's going to be a +1 when the edge is exiting V, and a -1 when the edge is entering V, right? And so just to fill this out some more, what do the columns of this matrix correspond to? Like, what do they index over?
All the edges.
Exactly, right? There's one column per edge, right? And that's why we have an identity matrix on the top, which spans all of the columns. And then we have these extra rows on the bottom, which take subsets of the edges. Okay?
Wait, I have a question. Does it matter the sign that we say for like the exits and the enters?
Not in this case, because we actually have an equal 0 constraint, but I'm just trying to be consistent with the way that I wrote the constraint in the linear program.
Okay, thanks.
Okay, good question. Yeah, keep those questions coming. If I double the tap, ooh, thank you very much for that lovely piece of advice. I did not realize that the pen separately accepted tap input. Thank you. Okay, so what happens now when we perform a transposition? Okay, so when we perform a transposition, we're going to be looking at a constraint for each, at a constraint corresponding to each column, right? And the question is, what are the coefficients that show up in that constraint? Which corresponds to a particular edge, VW. Right? Where do we see non-zero values in the column?
So there's like a 1 in the like rows corresponding to the edges, and then within the like.
Good. Wait. Let's take this one at a time. So if we look at the, I think you're pointing at the identity matrix, right? And saying that in the rows corresponding to the identity matrix, right, we're going to hit a 1 somewhere. And which variable is that going to correspond to? Which row are we going to see that 1 in?
The row corresponding to the variable for that edge.
Exactly. So we're going to have a 1 multiplying the YVW variable, right? Coming out of the identity matrix. Now, what else are we going to see as non-zero in this column? Well, the other thing we need to look at is the entries that are generated by the vertex rows, right? That correspond to the various ZV variables. So where are we going to see a non-zero in a vertex row?
In the rows corresponding to the variables ZV and ZW?
Exactly, right? So we got +1s and -1s on vertex V at the edges that enter and exit V, right? So conversely, if we look at a particular edge, it's going to have +1s and -1s at the vertex it enters and the vertex that it exits, right? And as we discussed, there's going to be a +1 at the vertex that it exits, right? So that's going to give us a +1 times ZV and a -1 times ZW. Yes? Which of course I can simplify down. I can ignore the 1s now and just YV plus ZV minus ZW. What's the right side of this constraint going to be? How do we figure out the right-hand sides of the constraints? Where do we look for the coefficients? Where do we look for the numbers that go on the right side of the constraints?
We're going to look at the objective function. So it's going to be 0 if it's not the TS edge, and it's going to be 1 if it is.
Exactly. We look at the objective function of the original linear program. We see that all of the coefficients are 0 except for the XTS variable. So this value is going to be equal to 0 for VW not equal to TS, and 1 if VW is equal to TS. Yes? Sorry, but I jumped the gun here. I don't know yet if that's going to be an equal sign. So that's actually the next question. What sort of equality or inequality do we use to relate the left-hand side and the right-hand side? How do we decide that? Well, we go back to the cookbook, right? And we see that the shape of the inequality comes from the shape of the inequality comes from the type of variable that we're working with, right? Non-negative, non-positive, or unrestricted, right? So if we look at our initial linear program, those are non-negative variables, right? XVW greater than or equal to 0. And as I discussed last time, a non-negative variable, a positive force, so to speak, corresponds to a constraint that is in the proper direction for the objective function, the natural direction for the objective function, right? So we go down and look at our linear program and we see we have a minimization. We have a minimization problem. So what is the natural direction for constraints?
Greater than or equal to?
Exactly, right? So since it's a minimization problem, the natural constraint direction is a lower bound that prevents things from getting small. So there are our constraints. Okay. Now the other question we have to answer is what kind of variables are these y and z variables, right? So are they non-negative, non-positive, or unrestricted? So we answer that question the same way by looking at the cookbook and by looking at the original linear program. So what can we say about the y variables, which correspond to the capacity constraints? Sorry, that correspond to the yes, that correspond to the capacity constraints. Are they non-negative, non-positive, or unrestricted?
Non-negative.
What was that?
Non-negative.
Non-negative. How come?
Because it's like less than or equal to in the dual program for the capacity constraints. So in the primal, it should also be less.
And less than or equal to, is that in sort of the right direction for the objective or the unexpected direction for the objective? Right, so the first linear program is a maximization linear program.
Right.
So an upper bound is what we would expect, right? To limit a maximization. So it's the natural direction of constraint. And that means that the dual variable to that constraint is going to be non-negative. So we go down here and write y greater than or equal to 0. Now, what about the z variables? Are those non-negative, non-positive, or unrestricted?
They're unrestricted.
How come?
Because they correspond to the balance constraints, which are equalities.
Exactly. Right. Now, it's important to notice that they're unrestricted because it's an equality constraint. The fact that the equal sign, that the value is 0 doesn't matter. It's just the fact that it's an equality constraint, which can't impose any force in either direction. So the z variables are unrestricted. And so I'm just writing this to be explicit. In general, I wouldn't write anything else at all about the z's. Okay, so now I have the whole linear program. I've got the minimization objective. I've got a small set of constraints, and some of the y's are restricted to be non-negative. So we've completed the dualization of our Maxwell linear program. Are there any questions about that? So the next thing that we do, now that we have completed that dualization, is we think about the interpretation. How can we use this linear program to understand more about max flow? Okay, so we've already seen that, sorry, this is a YVW, not a YV. Okay, so what we see here are variables on, actually, let me write it down in one place so we can stare at it. So we're talking about min of the sum of UVW, YVW, such that ZV minus ZW plus YVW is greater than or equal to 1 if VW is not equal to TS, sorry, greater than or equal to 0 if VW is not equal to TS. And meanwhile, ZT minus ZS plus YTS has to be greater than or equal to 1. And all the Y variables have to be greater than or equal to 0. Okay. So how can we interpret this linear program? We've got a value per edge, and we also have a value per vertex. Yes? But what can we understand these values to mean? So we can get a hint by looking at our constraints, right? This ZV minus ZW plus YVW is greater than or equal to 0. Does that seem reminiscent of anything?
It looks like reduced costs.
Yeah, in particular, it looks like a triangle inequality constraint, right? So what this suggests is that we can think about the YVWs as lengths. Okay, and if the YVWs are lengths, then the ZVs are distances that satisfy because they satisfy a triangle inequality. Okay. Now let me also notice that without loss of generality, we can assume that YTS is equal to 0. Okay, because YTS is being multiplied by UTS. And if you think about it, to make this a max flow problem, we would set UTS equal to infinity to allow as much flow as wants. However much flow gets from S to T, we'll want to send back to S. So we're just going to set UTS equals infinity to make room for that flow. And if YTS is not 0, then the resulting objective function is going to be infinite, which is certainly not the way you want to minimize an objective function, right? Now, once I tell you that YTS is equal to 0, your second constraint is now just requiring that ZT minus ZS should be greater than or equal to 1. Right, because there's no longer a YTS term. Okay. So this is basically just saying that the distance between S and T has to be at least 1. Yes? Now, another thing that you can see looking at this linear program is that we only ever look at differences between Z's, right? ZV minus ZW or ZT minus ZS. So we can really add a constant to all of the Z's and we have an equivalent solution with the same objective value. So I'm actually going to add minus ZS to all of the Z's so that in fact ZS becomes 0. Okay. So if you think about it, what we're now saying is we want to assign some lengths YVW to the graph edges. and we want to put S at position 0 and T at position 1. And we want to put all of the other vertices somewhere along the line from S to T. But the length of the edge, YVW, has to be larger than the space between V and W. Does that make sense? So this is what's called an embedding. Trying to embed the graph on a line. Make sense?
I have a question.
Yes.
The fact that ZS looks like kind of redundant, does that tell us anything about the primal LP?
Yes, it does, right? So if you think about it, the fact that the ZS is redundant is kind of telling us that our constraints are not linearly independent. And so we've already talked about how if you don't have linearly independent constraints, you can go in and remove some of them, right? And that's going to, transform this matrix a little bit by getting rid of it's going to get rid of the ZS row, basically, right? So if we're getting rid of the ZS row in the primal linear program, what is that going to do in the dual linear program? It's going to get rid of a variable, I think. But speaking more generally, it's going to simplify this linear program as well, or reduce it. I wouldn't say it's simplifying it, right? Because it says that there's some redundancy in the expression of this linear program as well. And you can see that because we have equality constraints, right? The equality constraints essentially would let you rewrite some of the variables in terms of the other variables and get rid of them.
I see. So since each edge is counted once and like going forward and counted once in the negative direction going backward, adding all the other edges gives you the balance.
Yeah, I mean, it's not actually about the forward and backward of a single edge, but that, right, if you know the value on all of the edges but one incident on a vertex, then you also know the value on the last one thanks to the balance constraints. So that last variable is redundant. Right, and you can sort of use that argument to get rid of, I think, a spanning tree worth of variables, and have a linear program with fewer variables. And similarly, you can have a dual linear program with fewer constraints.
Thanks.
Sure. Okay, so we're trying to embed this graph on a line. The trick is we have to pick the edge lengths. To fit the distances, right? Notice that once I place V and W, it's essentially putting a lower bound on the value of the edge, on the length of the edge, right? Now, what are we trying to minimize? This sum of UVW, which is a capacity, times YVW, which is a length. Now, we haven't talked much about capacity as a physical artifact, but if you think of these as pipes, right? What defines the capacity of a pipe is its cross-sectional area, right? Because that determines how much fluid can pass through it in a given unit of time, right? So what we have here is the cross area of the edge. And here we have the length of the edge. So what are we minimizing? What do you get when you multiply an area by a length?
Volume?
Volume. So this sum over all edges is the total volume of the network after you've assigned lengths to the edges. Okay? Now, where did that come from? What does that have to do with the max flow problem? Well, suppose that you send F units of flow. From S to T. And here again, a unit is sort of a cross-sectional area of that unit, of that flow. Okay. Because of the way that we've embedded the network, that unit of flow is one unit of length long, right? And also has 1 unit of cross-sectional area. So the volume of that unit of flow, which is being sent from S to T, is 1. Right? So just restating that, because I'm playing fast and loose with units, right? If I'm sending, you know, a unit per second of flow from S to T, then there's a certain amount of it that's going to be in the network, traveling from S to T. And by the units that I've just defined, there's going to be 1 unit of volume of that flow in the network at any given time. And this is true for each unit of flow. So what we've shown is that the objective of this minimization problem, right? The minimum volume of this network embedding which separates S and T by at least 1 unit of distance, right, is equal to the value of the flow, which is the volume of the flow in the network. Which is just saying that the flow has to fit. Right? So this argument about volume of flow is just articulating actually weak duality, right? We know from physics that the volume of the network in terms of the capacity of its pipes has to be larger than the volume of flow that's in the network at any given time. Okay? What strong duality tells us is that these are actually equal, that it's possible to create a network whose volume is equal to the amount of flow that you're sending from S to T. Okay, so how do we create that optimal volume network, right? How can you embed this network? How can you assign lengths to the edges so that the volume of the network is equal to the flow value? Well, let's see. In order to figure that out, let me introduce you to another important idea in linear programming, which is complementary slackness. Okay, I talked about this before, but now we're really going to leverage it. Does anybody have any questions about the dualization we did though? No?
Sorry, I have a question.
Yes, go ahead.
So I didn't quite get, so I guess we want, like we have a flow and we want to say that we can, you know, pick the edges somehow, that
Pick the edge lengths.
all conditions are satisfied.
Yes.
Can you explain how you actually create a flow for that?
Well, so the flow is the solution to the what I call the dual linear program, right? This is the solution to this linear program is the max flow.
Right.
Okay. And the primal linear program that I wrote over here is a program that tries to optimize the volume of the network, minimize the volume of the network. And again, what we basically have is a physical argument for weak duality. Right? If I give you some embedding of the network, which has a certain volume, right? we know that whatever flow I send through that network, each unit of flow is going to use up 1 unit of volume. So that tells me,
sorry, this argument, like, why does 1 unit of flow exactly consume 1 unit?
well, it has to use at least 1, right? Because it has to get from S to T. And so if we think about that unit of flow as being a tube of flow that is 1 unit wide, or it has 1 unit of cross area, and it has to run across a path that is 1 unit in length, then the total volume of that tube is going to be 1 unit of area times 1 unit of length. And so it's going to be a volume of 1. Okay. And of course, it's going to be broken up through multiple edges that unit of flow is traversing. But the total volume of all of those edges, or the amount that's being used by this unit of flow, is at least 1 unit.
Right, thanks.
Sure. Okay, so coming back to complementary slackness for a minute. So suppose that we are given feasible solutions. And I'm going to go back to our original notation now. X and Y for my primal and dual linear programs. Okay. We know that the optima are equal, but more generally, I'm going to define the difference between the values of the primal and dual solutions is the duality gap. Between these two solutions. Okay. And weak duality tells us that this is always non-negative. Strong duality tells us that it's 0 at the optimum. Yes? Now, let's take that LP that we started with, which had a sort of a max YB such that YA is less than or equal to C, right? I'm going to rewrite that into not quite standard form, but close enough. I'm going to write it as YA plus S is equal to C, and S is greater than or equal to 0. So I'm introducing slack variables into my canonical form LP. All right. Now I can take the duality gap, CX minus YB, and I can rewrite that as YA plus S times X minus YB, right? Just to remind you, our other linear program, besides the max of YB such that YA is less than or equal to C, we also had a min of CX such that AX equals B and X greater than or equal to 0, right? So if I take my duality gap, since YA plus S is equal to C, I can substitute that in. But I also know that AX is equal to B. So I can write this as YA plus S times X minus Y times AX. Yes? But now you notice that I have YAX twice. They cancel. And so the duality gap is just equal to the dot product of the slack variables with the primal variables. Okay. And recall also that S is greater than or equal to 0 and also X is greater than or equal to 0. So we have a dot product of non-negative values. This immediately tells us that Sx is greater than or equal to 0. But it also says, what happens if Sx is equal to 0? What can we conclude if all of the variables are non-negative what is it? How do we get a zero dot product?
If there's no slack at all.
Well, there could be no slack at all, right? All the S's could be zero, but is that the only way to get a zero?
Or
So
X. So, yeah, either S or X.
Right. Either SI or XI is zero. Okay. And this is an if and only if, right? If you're at optimum, then either SI or XI is zero. And conversely, if every SI or XI, one of them is zero, then you're at optimum. Okay. And this is the complementary slackness condition, right? At the optimum, SX is zero. I already wrote it, but that's called complementary slackness. Okay. And what's nice about this is that it lets you infer things about the solution, even if you don't know the whole solution, right? You can say, whatever the optimum is, either a primal variable is going to be zero or the corresponding slack variable is going to be zero. Now, what does it mean for the slack variable to be zero?
The constraint corresponding to that slack variable is tight.
Exactly. Corresponding constraint is tight, right? In other words, either Xi is tight as zero, or YAI is tight at CI. They cannot both be slack. And that's the complementary slackness condition. Okay? So let's think about what that means for our max flow problem. Okay, so remember our primal, it's been a while, so I'll write it back, I'll write it down again. Max XTS, sum of XVW minus XWV is equal to zero, sum over W, and XVW is less than or equal to UVW. And our dual linear program was min sum of UVW, YVW, such that, let me get the directions right, ZV minus ZW plus YVW is greater than or equal to zero. And ZT minus ZS is greater than or equal to 1. In fact, we set ZS to 0, right? So what does complementary slackness tell us?
That either an H flow is saturated or the corresponding dual equation is tight, meaning that the edge is stretched out in the embedding.
Exactly. We can relate the primal variables XVW to the edge lengths constraints in the other linear program. Okay. So let's consider, I mean, this is what we're doing, optimal Y star and Z star values. Okay. Actually, before I go here, let me go back to asking this question of what is a good solution, right? If you needed to solve the length linear program, how might you try to choose lengths to give you a good answer, a small volume?
I guess when the edge has large capacity, you want to make it shorter.
Yeah, that sort of is the intuition, right? Ideally, you would make all of the large capacity edges have length 0 so that they don't contribute to the volume at all. And you kind of want the small capacity edges to take up the slack, so they'd probably have to be length 1, right? So which edges should you make length 1? To take up that slack. You want the minimum volume overall, right? So
it makes sense to put VW equal to ZV minus ZW.
Yes, good point. So notice that in this linear program, we are always going to set YVW actually equal to ZV minus ZW, right? Because we have an upper bound on YVW, right? And we want YVW to be, sorry, we have a lower bound on YVW, right? Sorry, ZW minus ZV. Right, because we want to make YVW as small as possible so that the objective function will be as small as possible, right? But we can't make YVW smaller than that without violating the constraint, okay? So here's what I'm going to do. I'm going to take my optimum Y star and Z star, and I'm going to define a cut. S consisting of the vertices V such that ZV star is less than 1, okay? Remember, we did this embedding, right? We put the vertices in various places. What I'm proposing to do is draw a line just before ZV equals 1 and consider the cut of all of the edges that cross that line. Does everybody agree that that's a cut, an ST cut? Any questions about that? Okay, so I've defined this cut consisting of all the vertices that are not at distance 1 or that are closer than 1. Okay, now let's use complementary slackness to understand this cut. Okay, so notice that S is on this side because ZS is 0. And some other vertices might be on this side as well. So suppose that an edge VW leaves the set S. Okay. What does that tell me? Well, that tells me that YVW, which is equal to ZW minus ZV, right? By what we just wrote over here, or actually, it doesn't even need to be equal, but it's greater than or equal to ZW minus ZV. That's greater than 0. Why is it greater than 0? What does it mean for VW to leave my cut S?
So Z.
Go ahead.
So ZV is smaller than 1 while ZW is at least 1.
Exactly, right? So this tells me that YVW is greater than 0. Now, if a variable is greater than 0, what does complementary slackness tell me?
The dual condition has to be tight.
Right, the corresponding constraint is tight. What constraint corresponds to the variable YVW?
XVW most UVW.
Exactly. It's a capacity constraint. So to be tight, it actually has to be equal. Yes? Now suppose, on the other hand, that edge VW enters S. Okay. Well, in that case, we know that ZV is greater than ZW. We also know that YVW is greater than or equal to 0. That's just a constraint in the linear program. And that implies that ZV plus YVW is greater than ZW, which means that this constraint is slack. Right? Because we don't have equality. Now, if this is constraint is slack, what does complementary slackness tells us?
The corresponding variable has to be tight, or it has to be 0.
That's right. That implies that XVW has to be equal to 0. Okay. So what have we just learned? We've defined a cut, right? We define a cut. We know that every leaving edge is saturated. We also know that every entering edge is 0. And this just came out of complementary slackness, right? So if every leaving edge is saturated and every entering edge is 0, what does that tell us? What does it tell us about the value of the cut?
It's also the value of the flow.
It's equal to the value of the flow. So just by applying complementary slackness, we got max flow min cut. Right? Notice that any cut gives a dual solution here. Right? How do I transform a cut into an assignment of lengths to edges? Well, I just set YVW equal 1 for cut edges. And I claim that this is a feasible solution to this linear program. How come?
Excuse me, can I ask a question before?
Yes.
I didn't get, like, so the cut you defined is basically all other vertices than T in one side and T on the other side?
Not necessarily, right? This is vertices whose distance from S is less than 1. Okay. Now we know that the distance of T is at least 1, but there may be other vertices whose distance is at least 1. And those would also go on the T side of the cut.
And can you repeat, like, very quickly the two parts, like the...
Yeah, these are just straightforward applications of complementary slackness, right? I showed that if an edge is leaving, then the constraint on the length of that edge has to be slack, it has to be tight. Sorry, if an edge is leaving, I showed that the variable YVW has to be non-zero. In other words, it has to be slack, which means that the corresponding constraint is tight. That is, it's at its bound. So XVW is equal to UVW, the flow is equal to the capacity, the edge is saturated. On the other hand, if an edge is entering the cut, that means that V has distance greater than 1 and W has distance, V has distance greater than or equal to 1 and W has distance less than 1. And that tells you that the constraint is slack, which means that the corresponding dual variable has to be 0. So I conclude that every edge leaving this cut I defined is saturated, and every edge entering this cut I defined is 0. And that tells us that the value of the cut is equal to the value of the flow, just by basic flow conservation, right? Because all the flow has to get out and none of it can come back.
Right.
Okay. Now I also said more generally that if I take any cut and just call the cut edges length 1 and all the other edges length 0, this gives me a feasible solution where I can put all of the S side of the cut at 0, ZV equals 0, and anything on the T side I can put ZV equal 1. Okay. So every cut gives me a feasible dual solution, which tells me, again, that the value of every cut is larger than the value of every flow. But we also used complementary slackness to show that when we have optimal solutions, when we have a minimum cut and a maximum flow, their values are equal. Any questions about that?
So I
All
just
right. Sorry, go ahead.
yeah, so I was just wondering, like, could we just use strong duality to say that min cut equals max flow, or do we need to use the
Good question.
complementary slackness?
Good question. So weak duality tells us that min cut is greater than or equal to max flow.
Mm-hmm.
The problem is that in order to apply strong duality, we have to argue that the optimum solution to this linear program is a cut.
Oh, okay.
Right? It's possible that there's some nice solution that assigns fractional values to the y variables that might not correspond to a cut and that is better than all the cuts.
Okay, I see. Thanks.
Now, the construction that I did was specifically to address that, right? It took these possible fractional variables, but it generated a cut.
Mm-hmm.
And this is something we'll be seeing again. It's a technique called rounding, right? Because basically we started with a fractional solution, right? It's possible that these YVWs are fractional lengths. But after we generate the cut, there's a corresponding solution where the YVWs are 0 and 1, as I just discussed. So we've essentially rounded the solution to this linear program to an integral solution to the linear program.
But this wasn't necessary to prove that max flow equals min cut, right?
No, it was, right? Because again, strong duality tells us that these linear programs are equal. And certainly every flow corresponds to a solution, every solution to this linear program is certainly a flow, right? Sort of by definition of flow.
Mm-hmm.
However, every solution to this linear program is not necessarily a cut, right? Because fractional, it's not clear how to interpret fractional y values as a cut. But what I showed you how to do is to transform any such fractional solution into a cut. And that was necessary in order to prove that max flow equals min cut. And that transformation was based on complementary slackness.
I mean, the fact that like you proved that for an edge where the edge is saturated, then I mean,
yes. What I did was that I showed that that if you have an optimum solution that sort of corresponds to this, right? I defined a particular solution. If you think about it, what it tells you is that every min cut edge, that only min cut edges are allowed to be non-zero in the dual solution. Okay. However, if you have a graph that looks like this, okay, the optimum dual solution has value 2, but one such solution would put a half on every edge, right? So that's not real, that can't really be interpreted as a cut. It's more of a combination of two cuts.
Mm-hmm.
However, if I force the values to 0 and 1, that gives me a cut. And so that shows that max flow equals min cut.
I see. Thanks.
Sure. No, these are great questions. Okay, so for my next trick, I'm going to do the obvious thing and look at min cost flow. Okay. Now, the nice thing about this obvious thing is that we don't have to redo a lot of the work. Okay, because most of our linear program is actually min cost circulation. We already have a circulation linear program. So if I go back to my max flow or my max circulation problem, right? Here's my max circulation problem. What do I need to change in order to make it a min cost circulation problem?
Change the objective function.
Exactly, right? So I called this a max flow problem, but really what it was a min cost circulation problem where the only profit was on edge XTS, right? Because the constraints, those are just the balance and capacity constraints that apply to any flow. So all I have to do is change the objective function. So my new objective function is now minimize the sum of CVW times XVW, but I still have exactly the same constraints, that the sum of XVW minus XWV is equal to 0, that XVW is less than or equal to UVW, and that XVW is greater than or equal to 0. So basically the same linear program as before, just with a different objective function. So what happens to the dual? Right? I changed the primal by just changing the objective function. What does that do to the dual?
It changes the constraints?
In what way does it change the constraints?
So it's something like YVW plus ZV minus ZW is at least CVW or something like that?
Exactly. The point is that it doesn't change the matrix at all, right? We still have exactly the same shape of matrix. All that changes is that we have new coefficients on the right-hand side of the dual. Sorry, not the, this is the left-hand side of the dual. But we don't change the matrix, right? Remember that the objective function in one linear program becomes the right-hand sides of the constraints in the other linear program. So we only change the right-hand sides of the constraints. And that means I can write down the dual LP as pretty much the same as before. We now want to maximize, just like before, the sum of UVW, YVW. Why didn't this change? Well, because these coefficients come from the right-hand sides, which of the primal constraints, which haven't changed, right? And we have exactly the same constraints as before, namely ZV minus ZW plus YVW. But previously, this was bounded by 0 or by 1 for YTS. But now it's bounded by CVW. Okay. Now there's one other thing that you have to notice. Another change that I made in the original linear program was that I made a minimization problem instead of a maximization problem, right? We were talking max flow before, now we're talking min cost flow. So that's why the dual became a maximization problem when it was previously a minimization problem. But the other thing that changes is, since I'm now doing a minimization problem, now these upper bound constraints are in the unnatural direction, right? And so these become unnatural direction constraints. And that means that we get upper bounds for our maximization instead of lower bound. Sorry, wrote the wrong thing. Now that we have unnatural constraints, we are going to be requiring that the variables be non-positive instead of being non-negative. Okay. So did that make sense? We changed a max to a min, which meant that constraints that were previously natural are now unnatural, which means that variables that were previously non-negative become non-positive. Okay? So everybody believe me that this is the new dual linear program? So now I'm going to rewrite or change variables PV as minus ZV. And that lets me rewrite the linear program as maximizing sum of UVW, YVW, subject to the constraint that YVW has to be less than or equal to CVW plus PV minus PW. And also that Y is less than or equal to 0. Now, does this remind people of anything in min cost flow? This quantity, CVW plus PV minus PW, have we seen that before?
Reduced cost?
That's the reduced cost of edge E. Okay. So what this is saying, right, is that the reduced costs, sorry, what do I want to say? Notice here that we have a constraint that YVW be less than or equal to the reduced cost, and we also have a constraint that YVW is less than or equal to 0. So what that tells us is that YVW is equal to the smaller of the reduced cost and 0. Or in other words, it's the negative part of the reduced cost. So our objective function is just a sum of the negative parts of the reduced costs. Appropriately weighted. Okay. So now let me once again invoke complementary slackness. Okay. So suppose that a particular edge is not saturated. Whoops. A particular edge is not saturated, right? What does complementary slackness tells me? Well, the variable is slack. Or sorry, the constraint is slack.
Is it that YVW is tight at 0?
Right. Constraint is slack. And so that means that the corresponding variable, YVW, is tight. Sorry, is 0. Right? Now suppose that the reduced cost CVW plus PV minus PW is less than 0. Negative reduced cost. Well, that means that YVW is less than 0, right? So it's slack, so to speak. What does that mean?
That means that the variable is tight, or that like the edge is saturated.
Right, the constraint is tight. The corresponding constraint is tight. Which is to say that XVW equals UVW. What if the reduced cost, CVW plus PV minus PW, is greater than 0? Well, that tells me that YVW, which is at most 0, is going to be less than CVW plus PV minus PW, which means that the constraint is slack. And if the constraint is slack, that implies that the corresponding variable, XVW, is equal to 0. Okay. So what we've just shown is that if you have negative reduced costs, the edges are saturated, and edges with positive reduced costs are empty. And if you think back to our analysis of min-cost flow, that's exactly what we concluded in our study of feasible prices. Okay, so once again, just applying this cookbook method of transforming the linear program to its dual and applying complementary slackness gave us everything that we sort of directly derived in our study of max flow and min-cost flow. It gave us the sort of duality between max flow and shortest paths. It gave us max flow min cut, and it gave us feasible prices and their characteristics for min-cost flow. So linear programming is really a sledgehammer for understanding interesting things about combinatorial optimization problems. Any questions?
So complementary slackness was a result of strong duality, right?
That's correct. And in fact, you can use complementary slackness to prove strong duality. If you go back and look at my analysis, right? If you have a primal and dual solution that have complementary slackness, then you have equality of the primal and dual solutions. And vice versa. Okay. All right, so this completes our tour of duality and how it helps us understand optimization problems. Now, the next question we're going to study tomorrow is how do you solve linear programs? So finally, tomorrow, we're going to get back to algorithmic thinking instead of structural thinking. And I'm going to show you the sort of long-standing simplex method for solving linear programs, and then I'll sketch for you the ellipsoid algorithm, and not even sketch, but just briefly mention interior point, which are the 3 algorithmic techniques that are brought to bear for solving linear programs. So are there any finishing questions? No? Okay. Oh, announcement. Tomorrow, we're reshuffling the collaboration groups again. And so you need to make sure to, assuming if you want collaborators, you need to make sure to get back into the collaborator pool so that we can do that shuffle. Remember, again, the constraint that you're not allowed to collaborate with people who you've collaborated with more than 3 times on a p-set. Or sorry, that you've collaborated on with 3 p-sets or more. Okay? Great. I'll see you all tomorrow.